friends, let's have attention up here, please. We are going to do a lab today. I realized that I offered/promised you that at some point we would go over homework, and we haven't done that for a long time. And so I just wanted to check in with you. We can go over homework questions now if you have them, if they're kind of like at the front of your brain and you really want to talk about it, or if you would rather, we could wait and plan to do some homework tomorrow in class. Should we do that?
Yeah.
Question.
So is that for like this unit 7, and then when is that going to be due? So we need to trimester 3?
Yeah. Okay. Yeah. So I'll say this one more time just to make sure that everybody's clear. Okay. We will not finish this unit during trimester 2. Okay. So we are going to work on a lab that's going to last today and tomorrow, maybe also on Thursday. I don't know. It just depends on how fast we go. But I want to make sure that you feel good about this lab. This is like a big, chunky, like important lab. So we're going to spend some quality time with it. And then we've got like 2 more concepts. So like 2 or 3 days, and then we'll test. So we'll test over this unit next week. I can't tell you what day for sure, but we'll figure out which day it is. Is that okay? Are we excited about that? Okay. Enthusiasm about a test. Don't get that every day. All right. So let's plan to do homework questions tomorrow at the beginning of class. Does that sound fair? So if you haven't yet looked at homework, do it before tomorrow. That'll give you something to work on. And we're going to go ahead and start your lab now then, if that works. Okay. So why don't you send... No, you know what? Let's not send anybody anywhere yet. I want to show you the lab setup first so that you shh. Physicists, I need your attention again, please. So I've got my version of the lab up here, just like you have yours in front of you. So it says, given the apparatus shown, you and your group will investigate the question, how does affect the system's rotational acceleration? So what I want to know is what are some things that we could adjust in this system to measure as it relates to the acceleration? Henry, what you got?
Mass.
The mass. What mass?
The
The mass at the bottom of the string. So we could affect this one here, that mass there. Absolutely. We'll call that mass 1. I love it. All right. Other things that might affect the angular acceleration of the system. Yeah.
The balance of mass on the top.
What do you mean the balance of mass?
So instead of having 10 on one end and 10 on the other, you could have 20 on one end.
Yeah, let's not do that. That seems like and the reason I say that is because then it's not going to be regular angular acceleration. So one could do that. That's not the intention of this lab. But there are lots of other things we could change. And by lots, I mean at least 2. Go.
You can change the mass up on top as well on both sides.
Absolutely, you could. Yep. So we could change this. This drawing is a little different than ours, but like these guys here. Yep. So we'll call this, I don't know, what do you want to call these masses? Oh, you guys are so creative. Mass 2. So, and to be clear, the intention and the setup for this lab does suggest that the mass 2 values need to be the same, right? So if you have 100 here, you're going to have 100 here. Okay? Yeah.
Can you change the distance of the ring stand to the pulley?
Like this distance here?
Yeah.
You could. Do you think that's going to affect the angular acceleration? Probably not. So let's, I mean, and not that, and I want to make it really clear, because sometimes they do this in AP Physics, like on the AP Physics exam, where they might give you a problem like that, right? Where like this distance here, and it would be a problem, and you could actually write down the experimental procedure to solve that, or to answer that question, right? Your results might not be very interesting, but you could, absolutely. I'm going to suggest that it's not actually going to matter, and so I'm going to not include that one. Yeah. Did you have one, Henry? You look like you had your hand kind of up, but maybe I was dreaming. There's one other big one that I'm thinking of.
Where you put the mass on the stick?
Where you put the mass on the stick, on the top, on the crossbar of the T, right? Is that what you were going to say too, Nick? No. Okay, let me write this one down first. So that would be absolutely another one that we could do. So you could put could take these masses and instead of having them here, you could move them in. Right? So instead of having the masses where they're out in the green spots, you could move them in. Now, again, looking for symmetry because this thing is spinning, I am going to suggest that this distance here, what would we call that? Radius. I'll call it radius. Okay. So you could change the radius, but this radius and this radius need to be the same. Okay. So wherever you put it here, you got to put it there. Absolutely. What's up, Nick? You had your hand up before.
Oh, I was just saying, you change gravity.
If you want to fund the experiment such that we could travel to different places with different accelerations of gravity, I'd be all about that. I don't have the funding. I mean, budget cuts and like it's a tough. But yes, absolutely, one could. Yes, but again, not something that I think we can probably pull off. Are there any other things that might be obvious to change? Yeah.
The length of the string.
The length of the string itself. How do you think that's going to affect the acceleration?
It gives the mass one more potential energy so it can fall further.
Okay. So I could fall further. Because I totally agree with that, right? The potential energy would be greater because h equals 0 is further down. Is that going to affect the acceleration?
I mean, it applies the force. It wouldn't affect the acceleration.
What would it affect?
The maximum velocity.
Yes, absolutely. And that, again, I love the fact that we're having this conversation because absolutely the longer the string, the more distance it has, so the more potential energy it would have, right? So therefore the more kinetic energy it could have, and therefore the faster it could be going. But we don't want to know how the final velocity is affected. We want to know how the acceleration is affected. And the acceleration is just going to be the change in velocity over time. Is that okay? Yeah. Yeah.
So if you just lengthen the string, wouldn't you just be increasing the time that it has to spin?
Absolutely. Yep. And so by lengthening the string, you would be increasing the time, and then you'd also be increasing the final velocity that it's going at, the final omega. But again, if I drop, where did my frog go? Here he is. If I drop my frog from here to here, he has the same acceleration as if I drop him from here to here, right? It's just that he's going faster there because he's had more time or more distance to travel. But yes, you are right. Yeah. Yeah. All right. Any other ideas that you have for things to change?
We're changing the place where the string is located on this whole
On this part?
Yeah, so if it's closer to the top, would it change?
That's a good question. So, and this is something that we're going to get into more tomorrow. So my plan is to get us kind of started and get some data collected today. And then we're going to get into the nitty gritty of what we're going to do with this data tomorrow, because I don't want to sit here and talk at you the whole time. So the reason that I have it sitting up on books, that whole deal, is because I want it to be a completely horizontal force, so that all of the force of all of that tension force is acting on this thing to get it to spin. If I put this up higher, then I've got some of that force going down and some of it going horizontally, and then I have to do components. And yeah.
Would it change if you moved the whole pulley or system up and just had it still pulling directly at 90 degrees?
So if I put it like 7 books up and then had it up here,
Yeah.
I don't know. What do you guys think? Yeah, but it's a good question. I like these. Yeah, it's interesting, right? There's a lot of stuff that one can change in that. I don't think that would affect anything because that's just like changing kind of the nature of where your h equals 0. Yeah. Okay. How are we doing so far? Okay. So there are 3 big things that we might change. So how does blank affect the system? In that blank, it's going to be either mass 1, mass 2, or the radius, okay? And we're going to have different groups doing different things, so we can kind of compare what happens, okay? Now, things are your independent variables, right? So you're going to have one independent variable, the rest of them are going to be control. And then what's your dependent variable in all of these cases? The acceleration, right? So we need to figure out a way to measure that acceleration. And somebody asked that when we were over there, and we need to figure that out so that you know what to do. How are you going to measure angular acceleration? I heard lots of things, but I didn't, none of them, were loud enough to drown out everybody else. So somebody raise your hand and then tell me what you think you want to do. We'll start here, and then we'll make a big triangle. Go ahead.
Calculate the number of rotations at a certain amount of time and convert that to radians per second.
Okay, so the number of rotations per time, and then you said something else.
Convert that to radians per second.
And make that radians per second.
And then to find acceleration, you divide that again by time.
Okay, so this would give you an omega, okay? And we want alpha. So keep telling me more words.
Alpha is the change in omega over time. So if it starts at rest at 0 and then by 15 seconds it ends up at a certain omega, then you just change in the angular velocity over 15 seconds.
Okay. What do you guys think? Does that make sense? Yeah?
Yeah, you could just that, or you could just take the time going rotation and then go through some more.
Okay. Okay. My one concern about that, anybody know what my one concern is? Nick might have, or Kian, you guys can fight over it. Rock, paper, scissors, 4 to go. Go, somebody speak. Speak.
I just said, how would you measure omega? Like, how could you measure the maximum velocity?
How would you measure the maximum velocity? What do you mean?
Like, how would you determine the maximum velocity? Like, does you need that in order to determine acceleration?
Like for this one, you mean?
Yeah.
So Jasmine is suggesting to count the number of rotations in a given amount of time. But what?
It's going to be rotating pretty fast. It could be hard to count the rotations.
Okay. There's another but in there.
The amount of time it takes for one rotation decreases with time. So you're not really measuring the acceleration because that's the thing that makes it decrease.
Right. Does that make sense? So I like your idea, and it totally makes sense if we were going from one speed of 0 to one speed that's fast, and then it was going to stay at that speed. Absolutely, if it's going to stay at that constant speed, then counting the number of rotations over time makes complete sense. Because then and counting multiple rotations, that's all well and good. But every single rotation and every single part of a rotation, it's going to be speeding up faster and faster and faster. So that's not going to be a maximum. That's going to be at some point in the story that it's getting faster and faster. Right? So that's the little hiccup here. I like that idea. And I will be completely honest, every year that I've ever done this lab, that's like the number one go-to suggestion to start. It's another one of those good conversation things. More words from people. I'm going to go here and then here. Is that okay? Go.
You can measure how far the weight falls.
Measure how
Well, no.
Okay, hold on. No, I'm not saying you're wrong. I want to make sure I'm understanding what you're saying. So you're going to measure, say it again.
How far the weight falls.
Friends, shh.
The mass 1 falls.
Okay, so the distance that mass 1 falls. Okay, and then what?
The distance that mass 1 falls is equal to something with acceleration.
The distance is equal to something with acceleration. That is true.
Because you use g just because it's a known quantity of acceleration.
Okay, so here's a question. Oh my gosh. Okay, so here's a question. So you're saying you got that weight and it's hanging on the pulley and it's going to be going down and it's going to be accelerating.
Yeah.
Do you guys agree that the weight, this one that's yellow here, is going to be falling, it's going to be accelerating?
Yes.
Question for you. Is it accelerating at 9.8 meters per second squared? It's not. But you're on the right track to the way that I like to do this, but again, there are multiple ways to do it. So that I think measuring distance is an interesting idea. Even though it's not talking about the rotation part, it's still kind of interesting. Nick, you were going to say something, maybe related, maybe not at all.
Well, yeah, just, that equation, like the distance equals, initial omega times time, which would just be 0, starting at rest,
Mm-hmm.
plus 1/2 alpha t squared.
And what does that equal? That equals theta, right? Okay. Now, you could absolutely do that. And you could count it going around 5 times. 1, 2, 3, 4, 5. That's absolutely fair. And so then you would do 5 times 2 pi, right? Because it's 2 pi radians each of those rotations. And that would give you your angular displacement. Your initial angular velocity is 0. You would need to measure time for sure. So that would be absolutely a way to do it. This is all angular stuff, yeah? Is there a relationship? And so this top one here, totally fine. Question for you though. Is there a relationship between the acceleration that mass, what we're calling mass 1, as it's accelerating down, a relationship between that and the acceleration of the apparatus as it's going around? What's the relationship? Do you remember? A and alpha, how are they related? Are they equal? They're equal with a radius constant in there, right? Yeah. So you can absolutely do this and count your zoop, 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 count them 5 times or whatever, right? Multiply by. You could also, this is another way to do it, same kind of game, but I'm playing the game with linear motion because we understand linear motion really, really well. Vt plus 1/2 at squared. You with me there? You know, we actually did this lab a while ago. Do you remember that? We did this lab a while ago where it's dropping down a certain distance. We had a cart on the other side to find the acceleration a few months ago. Yeah. Initial velocity is 0. You can solve for the acceleration given the time. Yeah. Yeah. No big deal. Either one of these is totally valid, and they're good things to do. Is that okay? Is that kind of making sense? All right. Now you know what you need to do, right? Yeah. Grace is like, yeah, let's do it. All right. So this is what we're going to do. We're going to divide into some groups, and then we are going to assign some variables. You've got about 20 minutes, so you've got some time to get started.